Welcome to mechanics. So today's topics are a few prerequisites as usual, and then we'll go into the governing equations we need for solid mechanics. This is the balance of momentum and constitutive relation, strain displacement relationship, Hooke's law, we will assume. This gives us the strong form of the problem. And then as usual, we will derive the finite element formulation and look how the discretized systems that we obtain look like. And on the example of the solid mechanics system, we'll discuss the different analysis types you can use to tackle solid mechanics problems. Okay, let's start with the prerequisites. First, a bit of notation. In the slides, I use the dyadic product between two physical vectors, so vector A and vector B, simply by writing them next to each other. So I don't use the long notation with the outer product sign, and you should know that the product, the outer product of two physical vectors gives you a rank 2 tensor, so you can see this as a matrix. And this is the default in the slides. So let's look at an example, the outer product in 2D. We have two vectors with two components. So the vector V has components V1 and V2. And if you write them one as a column form and one as a row form, and you do the matrix product, you obtain the outer product, which is then a matrix with the component product. So V11, U1 at the position 1, 1, and V1, U2 at the position 1, 2, and so forth. Of course, this can be directly extended to 3D. So in 3D, it works the same. You write the two quantities and you obtain a 3 by 3 matrix or a tensor of rank 2. Then you should also know that the stress tensor and the stress vector, so the state of stress in the body is given by the Cauchy stress tensor, and we don't denote it by a sigma. It's a symmetric rank 2 tensor, we also know that, and in 3D it contains therefore 6 independent entries due to the symmetry. So it has 9 entries in total, but due to symmetry, only 6 are independent. And if we now know the complete stress state in the body at the arbitrary point given by the stress tensor, we can also compute the stress vector for any arbitrary cut surface. So if we do an imaginary cut in the body, there will be inner forces that are then seen as outer forces, so as a surface traction, and this can be computed by the inner product of the stress vector and the normal surface of the normal vector of the surface. This gives us our traction vector sigma n. So this is different naming for the same thing, the stress vector and the traction vector. These mean the same thing. And the dimension is, of course, the dimension of a stress, so a force per area. And it has 3 independent components in 3D, and they can be defined with respect to the normal vector of the surface, that we have 1 normal component and 2 shear components of the traction vector. So the governing equation for solid mechanics is the balance of momentum, and it's written here in equation 12. So we have the second time derivative of rho times u, where u is the displacement vector of any point in the continuum, minus the divergence of sigma, which is the stress tensor, we had it before, which equals a force density, so a given outer force in the volume. So this is a volume force density in Newton per cubic meter. And in fact, this equation is a conservation equation for the momentum density, which is rho u dot. So u dot denotes the first time derivative of the displacement vector. So this is the velocity vector. So let's look at the expression here. We have the divergence of the stress tensor. How do we build the divergence of a tensor? The rule is given here. Basically, this is the rule applies for the inner product of the nabla operator, which is a vector valued operator, with the stress tensor. And this you obtain by doing the sum product in the respective dimensions. So we have the x derivative partial x of sigma xx, the xx component, plus, and now comes the sum of the nabla operator times the first row of the stress tensor. So we have the first sum, and the second sum, it's the second row, and in the third sum, it's the third row. So we obtain a vector valued quantity. This is visible since we do an inner product. So the stress tensor, which is rank 2, multiplied with something, with a vector rank 1, and we have inner product, gives us a sum over one dimension. So we obtain a vector again. Okay, so this was the balance of momentum. The second thing we need to model solid mechanics is the strain displacement relationship. So how do the strains and the displacement, how are they related? And if we assume small strains, we can use the linearized strain displacement relationship given here in equation 13. So we have 1/2 of the gradient of u plus the gradient of u transposed. So the gradient of u in our notation is the outer product of the nabla operator with the vector u. So this gives us a rank 2 tensor, which is true for the strain tensor. The strain tensor as the stress tensor is a tensor of rank 2. And u was already mentioned, is the displacement vector. Of course, in meters, the strain tensor is dimensionless. So dimension could also be meter per meter, which is 1. So as explained, with the outer product notation is the default. This is clear if we have two vector valued quantities multiplied, we get the resulting rank 2 tensor. And we can also write this a bit shorthand as a B operator of U. So this is simply shorthand notation. This will be used in the following. So let's do an example. How does the strain tensor in 2D look like? We write the gradient U as the outer product. So we have the nabla operator here, partial x, partial y in 2D, times our displacement vector with the x and y component. And what we obtain is here this tensor valued expression with the partial derivative of ux with respect to x. In the first row, we have the derivatives with respect to x of the two components. In the second row, we have the derivatives with respect to y. Okay, and then we put this together. So we write down the expression for the small strain, for the linearized strain tensor, and we insert what we have. The second expression is transposed, and now we can denote these four components as the sxx component, sxy component, syx component, and the syy component. And you can see when you compare these terms that we obtain the usual expression. So sxx is simply the x derivative of the x component of the displacement. Similarly, syy, and for the shear strains, we have the mean between, 1/2 of the mean between the mixed derivatives. So uy, the y component derived with respect to x, and vice versa, the x component partial derivative with respect to y. And you can also see that we have obtained a symmetric formulation. Okay, and let's look finally at the small strain operator. Bu in 3D goes exactly the same way. We write the outer product of the nabla vector with u to build the gradient, which gives us this tensor expression, now a 3 by 3 tensor, and put together the equations for the strain tensor. And what we obtain is simply, again, the normal strains in the diagonal and the shear strains in the off-diagonal term. And as we know, also this expression is symmetric. Okay, so the final thing we need for modeling our solid mechanics problems is Hooke's law. This is the constitutive relation that we will use to relate stress and strain. Of course, we know that Hooke's law is only applicable for linear elastic material behavior. So the relation we have here is the stresses are equal to the double contraction of the stiffness tensor with the strain tensor. So the double contraction is here given in index notation. As with the simple dot product, this is a sum product over now 2 dimensions. So this is why we have 2 dots. We have 2 sums to do over the indices k and l. So this also tells us that our stiffness tensor is a rank 4 tensor, since it has to relate linearly a rank 2 tensor with another rank 2 tensor. And of course, we have written this in the most general possible formulation with a general stiffness tensor, which may be anisotropic, but still we consider linear elastic materials only. And depending on how the strain tensor looks like, of course, we can also use this to model isotropic materials, for example. Okay, and this already gives us the strong form for solid mechanics. We want to find the displacement field u of x and t satisfying our balance of momentum equation 15 under the constitutive law that we have assumed, Hooke's law, and the linearized strain displacement relationship given in equation 16. Of course, we want the solution over the complete domain omega we consider, and we want to fulfill the boundary conditions that we prescribe. And the boundary conditions can be either of Dirichlet type, so we directly specify the displacement field on the boundary gamma e, or they can be of Neumann type, where we specify the flux over the boundary, and this is now the boundary traction. So sigma in n is something known, is a known traction. And of course, since we have a time-dependent problem, we need known initial conditions for both the displacements and the velocities, since our equation is of order 2 in time. Okay, so now we have a strong form, and we already know how to derive the weak form of this equation. And this is done here. We derive the weak form for the mechanic PDE. The steps are as usual. First step, always multiply our strong form with the test function and integrate over the whole domain. So this gives us this integral expression here. The multiplication is done by your inner product. So we have explicitly to write the dot product here. And for the sake of brevity, we have omitted all the dependencies on the location x and time t. And now we need a new product rule, the product rule for the divergence here of the second term. I write it explicitly down, so the divergence of a vector valued expression in a tensor valued expression is written like this. we have the gradient of the vector double contracted with the tensor plus the vector unchanged inner product with the divergence of the tensor. Okay, and now we can actually recognize here the last term, which is the term we have here in our integral. And as usual, we want to replace this term and then apply the divergence theorem on the divergence term, which can be converted in the boundary integral, which is done here in the last expression. So what we have obtained by this is a shift of the differential operator from our unknown. Here we had the divergence and it was shifted to the test function. The next step here is to simplify this gradient u prime term, and this is done in the following way. First, we can split, we know that we can split any tensor tau into a symmetric and an antisymmetric part. And the rule is given here. If we know tau, we split it in the symmetric part. This is tau plus tau transposed, or 1/2 of this. And the antisymmetric part is tau minus tau transposed. And again, we take 1/2. So we can recognize the first form is actually our B operator, and the second form, the skew symmetric part, we call W of U prime. And then we can also see that due to the symmetry of the stress tensor and the property of the double contraction, where we simply do the sum over all the component products, we can show that the double contraction of something symmetric is equal to the double contraction of the thing transposed. So this holds for any tensor tau. And if we now insert our relation for WU, so this would be the second term if we split the gradient U prime double contracted with the stress tensor. This is the second term, and we can show using the above relation that this is actually 0. So therefore, we can write, if we insert these two rules, we can write instead of the gradient of U prime, simply our B operator of U prime. So this has simplified the equation a little bit. And the final thing to do is to insert the expression for sigma, so our constitutive relation. So here we will put in the strain displacement relation and Hooke's law both at once. So the sigma is transformed into C double contracted with B of U. And the final step, as usual, is to incorporate the boundary condition. So the boundary integral can be replaced by all known boundary terms. We know that the Dirichlet terms will be neglected since we don't have to test there. And the Neumann terms will go on the right-hand side since they are known. So what types of boundary conditions do we have? Again, a repetition, we have displacement boundary conditions. They have to be given at the boundary gamma E and be known in time. This is important for time-dependent problem. And we can specify the traction at the boundary. So this is a Neumann type condition where we specify sigma in n to known values. So this would be a known traction. And of course, the natural boundary condition is actually sigma in n equals 0. So the homogeneous Neumann condition. And this means physically a stress-free boundary. So this happens whenever you don't specify any boundary condition, you require the boundary to be stress-free, which is typically what you want if you do solid mechanics problems. Note also that the boundary traction vector has 3 components, as I already said, 1 normal and 2 shear tractions. And for example, a pressure load would be simply a special case defining only 1 component being the normal component, and you can write it the required stress vector as minus p in n, where n is the normal vector of the surface. So finally, we have the finite element formulation, so the weak form for solid mechanics. Given an initial displacement field and velocity field, u of x and u dot of x at time 0, find the time evolution of the displacement field u such that our integral equation here is satisfied for all test functions u prime of x. Again, for all test function is important and enables us to use the Galerkin procedure to obtain a discretized system. So what steps do we do in this finite element procedure? We introduce an ansatz function for the test function and the unknown function. Note now that we have vector valued ansatz functions for the 3 components of the unknown coefficients in the 3 spatial dimensions. So to write it out in 2D, because it's a bit shorter, we approximate the x component by here the x component. So we have a sum of ansatz functions for the x coefficients in the 0 here, so we don't mix them. And for y, we take the same ansatz functions again. So this is how we apply this vector valued boldface notation here for 2D. And then we can apply the usual Galerkin procedure, which yields a discretized system. So let's look how this discretized system looks like. We will obtain a mass matrix multiplied by the second time derivative of our unknown vector x here. We will obtain a damping matrix that is multiplied by the first time derivative in the stiffness matrix, which is multiplied by the unknown vector x itself. And on the right hand side, we obtain a forcing term f, which consists of the boundary terms and the volume forces. So this is a system of coupled second order ordinary differential equations. The vector of unknowns contains all the nodal displacements. So x contains displacements. In the case of solid mechanics, we have mass, damping, and stiffness matrix, and the forcing vector, I already mentioned that. And we can numerically integrate this system in time for given initial conditions. Note also that the damping matrix D was not present in our weak form, so we have not assumed any damping. If we want a damping model, we need to assume something. So either within our continuum modeling, but Hooke's law doesn't provide any damping, and a frequently used damping model is the so-called Rayleigh damping, where the damping matrix is simply made proportional to the mass and stiffness matrix by 2 coefficients alpha and beta. Okay, so finally we can look into the analysis types. So we have our equation system, ordinary differential equation system. Now the time derivative written shorthand in the dot notation. And the simplest possible analysis type is the static analysis type, where we simply consider time independent problems. The x dot dot and x dot are assumed 0, and we can simply solve the linear system kx equal f. The second analysis type is the eigenvalue analysis, where we assume free undamped oscillation. and want to compute the possible solutions which are obtained by solving this generalized eigenvalue problem here. We have the case of harmonic analysis, where we assume harmonic forcing, so sinusoidal forcing for the right-hand side term, and then we can deduce that we will look for the steady state solution X by again solving a linear system. And the most general case is the transient analysis, where we have given initial conditions and known forcing vector, and we simply integrate forward in time, typically by solving one linear system per time step. So let's look a little bit in detail into the static analysis. So what are the assumptions? The forcing vector has to be constant over time, otherwise static analysis is of course not applicable. And we can compute directly the stationary point, so the time derivatives are set to 0, and this is done by solving one linear system. So this may be appropriate for sufficiently slow forcings, and usually what you have to compare them to is the dynamic response time of the system. So this can be deduced for the eigenfrequency from the eigenfrequencies, which we will compute in an eigenfrequency analysis. The harmonic analysis. The harmonic analysis, let's look at this next, is solving the equation system given here. So how is this equation system obtained? The steps for the derivation are now given here. So the first assumption is that the forcing has to be harmonic. So we can write it as a complex valued amplitude, so f hat, times e to the power of j omega t, where j is the complex quantity. This is the complex valued notation for a harmonic signal. Of course, the actual physical signal is only the real part of this, but the complex notation is used for convenience. And if you plug in this ansatz and do the same ansatz for the unknown x, you obtain the following equation. So we know that if we have a damped system and we force it with sinusoidal excitation, it will reach an oscillatory steady state for arbitrary initial conditions. Therefore, we can directly in the harmonic analysis compute this steady state. Of course, the solution is dependent on the forcing frequency omega. We can already see this because our generalized system matrix here, k plus j omega d minus omega square m, is dependent on the frequency. So naturally the solution will also be frequency dependent. That means we have to solve one complex valued linear system per frequency we want to obtain the harmonic solution at. So the solution, of course, will also be a complex valued, and this complex valued solution actually encodes both the phase and the amplitude of the oscillation in the complex quantity. So if you want to look at this into more detail, you can simply write down the expression here, expand the e to the power of j omega t into sine and cosine, do the same for the complex quantity, write it as real and imaginary part, take only the real part of it, and you have the actual physical signal in the time domain again. The eigenvalue analysis is very similar from the derivation point of view. What we also assume in the typical eigenvalue analysis is an undamped system, so the damping matrix is 0, so our equation reduces to this form, and also we only consider free oscillations, so no forcing. That's what meant by free. So we set the forcing vector on the right hand side to 0, and what we see is we obtain an eigenvalue problem, and solving this eigenvalue problem only gives us the admissible solutions for these assumptions of undamped free oscillation. So if we solve this generalized eigenvalue problem for the eigenvalues lambda corresponding to omega square here, we will get the natural frequencies from the eigenvalues and corresponding oscillation mode shapes. And finally, we have the transient analysis, which is simply obtained by solving the most general ordinary differential equation system in the discretized form. So if we have given initial conditions for velocity and displacement and discretize in time with time steps delta t, we can integrate numerically using an appropriate scheme. For example, a Newmark scheme or a Hilbert-Hughes-Taylor scheme. The derivation of both schemes is very similar to what we've done for heat conduction, and is not the main focus of this course. So essentially, you should know that we have to solve one linear system per time steps if we apply an implicit scheme, which is recommended due to stability consideration. So we have to solve a new linear system for every time step and then compute the next for the next time step.